Producing a certified reference material requires locking an instrument into a testing cycle that consumes weeks or months of continuous machine time. Achieving ISO 17034 compliance is the requirement for ensuring metrological traceability, but executing it demands a steep operational investment. Consider classical stability monitoring. You pull stored samples every few months, run dedicated tests, and constantly recalibrate to account for day-to-day instrument drift. Then there is multi-laboratory characterization, where you package samples, coordinate shipments across dozens of external facilities, and attempt to normalize the resulting variance. Laboratories are trapped. Meeting strict legal requirements to prove traceability forces them to absorb heavy financial losses from machine downtime and administrative bloat. ISO 33405 provides a specific playbook to optimize this process. It outlines exact procedures to bypass the most expensive certification steps before costs rapidly scale up. We will look at two specific alternatives from this standard: isochronous stability studies and single lab value transfer characterization. These approaches require strict material prerequisites to function legally under ISO rules. You cannot apply them to every batch. You trade the flexibility of testing diverse, complex matrices for a massive reduction in analytical drift and machine time costs. Mastering these two tools allows a lab to systematically outperform traditional certification methods in both cost and precision. Proving a material's stability over its intended shelf life is a primary driver of cost. The flaw in classical stability testing is the timeline. Because you test repeatedly over months, day-to-day instrument calibration drift can easily be mistaken for actual material degradation. The split-screen graph maps the isochronous alternative against the classical model to show how we solve that drift problem. The isochronous method requires storing your units at extreme reference temperatures to completely suspend material degradation. Instead of testing incrementally, you defer all measurements until a single analytical run at the very end of the study. You make all measurements under strict repeatability conditions on the same day. This produces a tight cluster of data, eliminating long-term measurement drift entirely. The ISO standard explicitly defines this method's trade-offs. By deferring measurement, you cannot identify instability until the study is complete. Additionally, if the material changes progressively under freezing conditions, it leads to an incorrect conclusion that the material is stable. Isochronous studies require you to trade your early warning detection for ultimate analytical consistency. Assigning the certified value and its standard uncertainty to a material presents a similar bottleneck. The traditional approach demands characterizing a measurand using multiple methods across a network of competent laboratories. This comparison matrix places the multi-method approach against a highly efficient single laboratory alternative, characterization by value transfer. Value transfer scores perfectly on scheduling effort and cost because you directly compare a candidate CRM against an already characterized primary CRM. But notice the strict warning under matrix flexibility. Value transfer requires CRMs be closely matched to make material-specific bias negligible. For example, characterize a cadmium solution against a certified cadmium solution because the matrix is identical. Do not characterize cadmium in granite against a pure solution. The differing matrix introduces an uncalibrated pretreatment variable. When the matrix is identical, metrological traceability is passed directly. The secondary CRM inherits its traceability to SI units through calibration with the primary CRM. Ultimately, value transfer allows you to bypass complex inter-laboratory logistics entirely, provided you strictly trade away matrix flexibility. You can evaluate your own pipeline against ISO 33405 rules immediately. This flowchart models the decision process. The first critical node is simple. What are you certifying? If you are certifying a pure substance or a simple solution, deploy value transfer. If you are certifying a complex or novel matrix, you must use multi-method or network characterization. The second decision node dictates stability. Can the material freeze safely without progressive physical changes? If yes, deploy isochronous stability. If no, you must default to classical stability monitoring. These advanced approaches only function when you maintain complete control over uncalibrated pretreatment variables and physical degradation. Commercial testing labs producing secondary CRMs, like trace element solutions, who possess ultra-low temperature storage, have a perfect fit profile for these methods. Primary metrology institutes creating novel natural matrix CRMs must absorb the high cost of traditional methods to ensure safety and compliance. The utility of isochronous designs and value transfers lies in their ability to isolate and remove the two biggest variables in metrology: time-based instrument drift and complex matrix bias. ISO 33405 transforms standard uncertainty into a strategic design choice, where the laboratory manages the final value through the specific architecture of the study.